Welcome to the 2015 NASA Ames Summer Series. We are curious about our surrounding. Curiosity is an innate behavior that we have. That behavior drives exploration and our need to explore. Exploration of new places on Earth here or faraway places in space is important for our survival. It's the way that we evolve. But an evolvable system is what we need for space exploration, one that advances us to eventually get to Mars and beyond. Today's talk, entitled Pioneering Space Evolvable Mars Campaign, Architecture Studies on Carrying Out the Journey to Mars, will be given by Jason Crusan. Jason is the Director of Advanced Exploration Systems Division at NASA headquarters. He has a bachelor's degree in electrical engineering and physics and a master's degrees in computers information systems. He is also currently a PhD candidate in engineering management at George Washington University. For those students, realize that while he is at headquarters, he's still continuing his education to receive his PhD. Please join me in welcoming Jason Crusan.
Thank you, guys. Glad this will be probably easier than a dissertation defense on those kind of things. So I'm going to talk to you a little bit today about what's been going on in human spaceflight planning at NASA. And you may hear a lot of terms like Journey to Mars, Pioneering Space, Evolvable Mars Campaign. And what I'm going to try to attempt to do is give you a little construct or what do those things mean and what's actually really going on that we have. So to start that off, we obviously use in a lot of our talking points and visual graphics, this graphic that you see up here, the Journey to Mars graphic. And it's great for kind of communicating to the general public about an overall strategy, but it lacks kind of the detail of what's really going on and how we make this transition from where we're at today to getting to Mars. So I actually draw your attention to the very bottom of the chart, which I think is the most important piece. And it talks about this transition from Earth-reliant through a proving ground period of time and space into moving on to being Earth-independent. So I'm going to kind of walk you through that thought process today and what that means. So when people think about human spaceflight, this is an iconic image that comes to people's mind. There's a famous photographer taking a picture of somebody coming down the steps of the LEM, Buzz Aldrin, stepping onto the surface of the moon. People think about this construct. It was Apollo, get there first, plant the flag, less than 10 years. It was a very kind of singular goal in nature. We ran that duration of the Apollo program. The Apollo program stopped, not because we ran out of hardware. There's some really good museum pieces at 3 or 4 locations around the country of actual flight hardware that never did fly. We didn't run out of hardware. We ran out of a will to go. And much of that I would attribute to kind of a myopic view of a singular goal of where we're at. So I'm going to step into where we're at today, fast forward to the space station era that we live in today, and what also we term as Earth-reliant. The space station is fundamentally different than what we saw during Apollo. It's not a singular goal. It's arguably 4 goals in the way I lay it out. It's obviously advancing the technology and systems to sustain human presence off the planet, all the technology work that's going on there. It's allowing us to understand the fundamental biology of the human system living off the planet, and what does that mean to actually live off the planet. It's allowing us to do fundamental research and development of understanding effects that the lack of gravity in the space environment actually emphasize in order for us to understand scientific fundamentals that are benefiting us back here today. And the 4th goal is actually another one that people kind of miss, but it's building an off-world economy. And how do we actually build a low Earth orbit economy or a true space economy that's out there? So you see this human spaceflight went from this kind of singular goal, plant a flag in less than 10 years, fast forward to today, to a very complex human spaceflight endeavor that we have with these multidisciplinary and multi-economic goals coupled with scientific goals of living off the planet, but we're very much in this Earth-reliant phase. So 10 to 15% of the global launch business goes to resupply the space station on a yearly basis. We can get crews back in less than 17 hours if there's a medical emergency. Cargo flights, now it's relatively routine to see a launch and 6 hours later docking. But there's that high supply chain and logistics chain that's out there. So one of the things as we extend human presence out there is it's much more about the logistics than a lot of other things that weigh on us. So keep that in mind. So you fast forward again to our current administration and a talk that he gave down at Kennedy Space Center in April 2010. Most people talk about asteroid by 2025s and Mars vicinity in the 2030s. Okay, let's not harp on that piece, but let's actually pull back what he said right before that, which most people didn't pay attention to. And I'll paraphrase it in my own words, which is extended human presence further and further and staying for longer and longer in space. Those two kind of fundamentals, go farther and stay longer, I think are in the air of how we're actually designing our human spaceflight exploration program today. And it's not just exploration anymore, it's about that extended human presence. And in fact, in the 2014 strategic plan, because NASA does strategic plans, you may not have actually looked at it, but in there was the first time we actually wrote a human presence into the solar system, the surface of Mars. By the way, that's the first time it's ever been written in our strategic plan, to my knowledge. And for this multiple kind of focuses, advancing exploration, science, innovation, international, and the humanity, and benefits to humanity. So again, kind of a rephrase of that kind of complex nature of what human spaceflight is today. So how do we go from this Earth-reliant phase to being Earth-independent? Well, we don't just do that overnight. We don't build the systems. We're learning a lot from space station, but we're going to need to figure out where to assemble things, where to live off this planet for extended periods of time. And we call this the proving ground period of time. Some people refer to it as a space, physical, an actual location in space. In our nomenclature, it's in cislunar or the lunar distant retrograde orbit, L1, L2, whatever you want to call it in the cislunar space. It's a location by which we can advance all the systems, but more importantly, it's the location that will actually build our spaceships to take us to Mars and also return them and park them on the way back for the next trip going outbound. So this is an artist rendition that's actually physics correct of seeing ourselves out at a lunar distant retrograde orbit with the moon there and the Earth off in the distance, working on one of those habitation systems and transportation systems that would take us to Mars and back. This is all in a stepping stone kind of build-out approach that allows us then to move into that Earth-independent phase. But we don't do that through just guessing on what decisions we need to make. We actually put together a set of guiding principles on how do we make decisions of what investments we need to make. How do we as a human spaceflight or a total space community make some of those decisions? So we put together some strategic principles that we think are pretty robust on what we think are the drivers to make all these decisions. So I'll walk through these briefly because it's good to spend some time with them. So one of them is the budget reality that we live in. Let's not design a human spaceflight endeavor or pioneering space or exploration endeavor that counts on some unrealistic budget allocation coming to NASA or the global community and budgets. There's been a lot of people over the years that have talked about, oh, if you just had a better plan, somebody will give us the money. There's been a lot of smart people that have tried to do that over the past decades, and that's not been the reality. So instead of kind of quibbling about building a better plan, let's actually start doing things. But let's do them in a way that we can actually do it without having to ask for the additional budget authority today. And we believe that we can actually do that with the budget we have. The next one is exploration enables science, science enables exploration. This is a quote from the late Mike Wargo, our past chief exploration scientist. And he'd like to point out that science and exploration are not against each other, but rather additive to each other. And by concentrating on them working together, we'll do a lot more. And this kind of harps on that principle that we have. Next is technology readiness. So we're now obviously going to apply technologies that are ready to actually implement the missions today, but we're not going to cut our seed corn for the next generation of technologies that we need to keep on expanding that horizon into the solar system. So how do we have a balanced technology portfolio? Near-term mission cadence, that's also not design an overall plan for human spaceflight that has long periods of time where there's no flights going on, like we have today. We've made that mistake several times. Let's not make it once again. And how do we keep a kind of a marching cadence of missions on a regular basis, because there's nothing more inspirational than actually flying hardware and flying our missions. So how do we design that cadence to be engaging? Commercial business. Very much talked about building the low Earth orbit economy with the ISS. A lot of that we got into after we had already completed station completion and all that. So let's actually figure out how to do this whole pioneering endeavor by involving the commercial sector from day one, instead of the reverse, where we traditionally do at NASA. So how do we leverage the actual space economy, the commercial business that's out there, and actually baseline that as part of our overall plans for all of our endeavors? The other piece is multi-use and evolvable space infrastructure. This means two things. Let's not throw away hardware, which we have a tendency to do in the space program. Fly something, throw away 80% of it, or if not 100% of it by the end of the mission, but rather let's build infrastructure that's reused over time. We've now demonstrated in the habitation world, at least, that we can build 30-year habitation structures. The space station in its lifetime will be in there over 30 years of actual certification and flight. And most of the components can be changed out and retrofitted and upgraded over time. So let's keep that kind of mantra with whatever we're doing. The second aspect of this is if there is something that we need to throw away or something that we need repeatable design, how do you do that once and kind of the assembly line approach of reflight of the same hardware over and over and modularize your designs to a point that you can maximize reusability. The last is we're not going to do this alone. We're going to do this with our international partners, leveraging the current ISS partners, but then building upon those partners and expanding to all the emerging space organizations that are out there as well. And with that, we've been a concerted effort over the past couple of years. We have what we call an International Space Exploration Coordination Group. They've designed and developed what we call our Global Exploration Roadmap. So what you see here is the front cover of that. But more importantly, you see the list of 7 items on the left-hand side there. And we actually have, among the 14 countries at the table, a common understanding of what the goals are for exploration around the world, not just at NASA, but all of our international partners. And that's a huge accomplishment to actually get global space leadership to agree on what the commonality of all that is. The other side of it is we also got agreement on what we don't know related to strategic knowledge gaps. So there's a bunch of things that we need to know about places that we want to go before we go there. That weighs into our engineering knowledge, it weighs into our overall architecture planning. Are there resources there that we can gather and utilize on trips in the future? Will the environment cause hazards for our humans when we send them there? So we've actually developed a whole set of strategic knowledge gaps, worked with the 3 assessment bodies for lunar, Mars, and small bodies, and got commonality there and understanding, and then worked that with the international community, and came up with a whole set of findings of where do we see commonalities even across all the destinations that are out there. And this is kind of a short list of those kind of things. But all that is public information and posted actually on all 3 of the assessment groups, and we're constantly revisiting that data and as we get and close actual strategic knowledge gaps as well. With industry, I talked about the involvement of commercial industry. One of the things that NASA's been doing a lot lately is running a whole series of RFIs, BAAs, non-traditional procurement things of how do you ask commercial industry how they want to participate with this. So the most kind of visual things are things like commercial cargo and commercial crew in our CASIS organization working on National Lab. But then you see emerging things like our asteroid redirect mission, BAA, which was looking into optimize our design choices to maximize commercial involvement in the asteroid redirect mission, to things like Lunar Catalyst, where we're not building lander capabilities ourselves, but rather helping accelerate the commercial industry's ability to provide that capability in the future. To things that are farther reaching out, like Mars Telecom RFI, where we're asking the public sector, how would you implement telecommunication services commercially for Mars and along the way to Mars? How do we evolve the ISS? There's another ongoing discussion of how do we evolve from a government-owned and operated space station to commercially owned and operated space stations over time. And that's an ongoing dialogue between us and the commercial sector. And then lately we've been moving into things like additional calls related to the asteroid redirect mission on follow-up with a commercial strategy for that. And then most recently our next step BAA, where we ask people to give us synergies between advanced propulsion systems that we want and commercial industry wants, habitation systems, and even the small satellite industry on that as well. And I'll actually touch base on a few of those investments that were and selections we made from that recent announcement. So if you think about this big philosophy change of human spaceflight and the whole fact that you want to actually analyze against all those strategic principles, we have an activity called the Evolvable Mars Campaign. What it is not a plan to actually set out every mission from here to Mars. We're not going to do that, because the fact is, as soon as you publish it, it will be wrong. We've done this in the past. We call it Design Reference Architecture 5.0. When it was written, we hadn't discovered water on the moon. We haven't discovered water on Mars. There's a whole host and series of other design trades that were in DRA 5.0. And as soon as it was published, scientific and technology advancement eclipsed its relevance. So rather, what we're using the Evolvable Mars Campaign is a series of trade analyses to help us make really solid near-term decisions in the next, say, 5 years, things that we actually have to budget for, make the acquisition choices and how we work with industry in the next 5 to 10 years, and actually explore that with the industrial and international partners and get that kind of queued up as the next things we need to do. And then the kind of 10-year and out work, how do you then make sure whatever decisions we're making today or in the next 5 to 10 range with the industry folks, how do we make sure that that doesn't get us to a point that we can't continue on in our whole overall journey to Mars and this whole pioneering space? So make sure we don't have any dead ends and kind of follow that through. So some things that we're looking at are, how do you split apart habitation capabilities? How do you optimize for LEO commercialization hab and exploration class habitation at the same time? Where's the commonality of those kind of systems? So split habs versus large monolithic habs. Cargo pre-emplacement. So how do you pre-emplace systems at Mars instead of having a whole sequence of missions kind of clumped up together that you have to do all your deployment? So things like that we're analyzing. The Evolvable Mars Campaign is made up of a whole series of NASA centers, including here at Ames, and also the various mission directorates, both on the science side and our technology side as well. Our international partners through what I said, the International Space Exploration Coordination Group, industry through all these RFIs and such, and then strategic knowledge gaps, working with our assessment groups and the scientists and understanding where we need to answer some key questions for these overall architectures as well. So on the left-hand side, what you see here is what we've done in the past and what is continuing to be done. There's a lot of architecture studies out there. Design Reference Architecture 5.0 is one example. If somebody asks us how we're going to get to Mars, that's one example of how you get to Mars. There are a whole host of other ways to do that as well. And we have these design reference architectures, and we're going to continue to have them. Many of your students in the group, many of your university senior projects and all that are also going to be doing design reference architectures. These are great. We should encourage this, the more the merrier, looking at the entire trade space of options that we have out there. What we then use is the Evolvable Mars Campaign to actually analyze that entire trade space to help us make concrete decisions of real missions to fly in the near term, and then do that overall long-range planning. Not set every single step from here for the next 30 years in stone. So this is that kind of parallel of how these work together and what we have going on. So I'm going to actually touch on some of the results of some of these studies. So in FY14, we were actually catching up a lot of our knowledge related to destinations in the Mars vicinity. So what do concepts of operations look like at Mars? Things like even Phobos operations. We didn't understand what that would look like and hadn't done a lot of work in that area. Transportation and trajectory staging point analysis. How do we get to the lunar destined retrograde orbit as the staging point versus LEO versus pick your favorite orbit, L1, L2, and all those kind of things. How do we get to where we're at with that? Looking at habitation and our overall Mars habitation strategy. Looking at the solar electric propulsion system that is proposed for the ARM mission, and how does solar electric propulsion fundamentally change the way we do cargo pre-emplacement? Again, this is another difference. When DRA 5.0 was written, we had dreams of maybe 5 kilowatt SEP systems. They have made incredible advancements both within the government and also within industry. And now we can imagine multi-tens of kilowatt solar electric propulsion systems that we couldn't imagine back then being ready. Other things like we're building SLS. wouldn't it be great to actually send cargo along with the crew, or have that excess capacity of SLS be utilized to do some of that cargo pre-emplacement? So what does co-manifesting look like? And those sorts of things. So all this helps us actually set up what are some of our proving ground objectives. What do we need to learn about in this time period? What do we need to learn about in cislunar space before we're ready to go? There's a list of things up here. I won't read them to you, but things like living in deep space for a long duration, how to do some of these semi-autonomous operations that we may have. It's a slightly different operational model that we have. Actually conducting EVAs in deep space. We haven't done that in a few years. And actually this whole large-scale robotic systems and human systems working together, and how to do deep space trajectory flight is another challenge that we have working on. People talk about, well, when are we going to Mars, and where does going to Mars mean? If you notice that the talk, when the president announced it, he said Mars vicinity in the 2030s. So we have a lot of talk about, does that mean Mars surface, Mars moons, Mars orbit? Quite frankly, it doesn't matter at the stage that we're at today. We need to be able to figure out the way to get from here to there into the Mars system. There's a lot of commonality that we can work on right now, and we can actually put off the final decision of where we're going for some time, and that's okay. And we can concentrate on all the commonality of those type systems. So to give you an example, in long duration habitation, we've been looking at transit versus Phobos versus surface, trying to find the common ground and habitation systems. Yes, there's gravity dependent components and some have stuff, but a lot of the components are actually, you don't need to actually figure out where you want to go. That a lot of the transit systems, which is what you're going to need first, are actually extensible to all the other areas. So how do you concentrate on the common ground and then leave the small changes for the future that you need to do to make that change? So I talked about where do we do assembly. We have people talk about a lunar distant retrograde orbit. This is a graphic to kind of show you visually what gravity wells really mean in a relatively simple way. So you got Earth there at the center and with its gravity well. You kind of come up the circles there and you kind of see where ISS is sitting in its orbit, and you see the geo belt out there near L3. And you kind of see their relative gravity wells. You see Moon out there, you see the Lagrange points, and you see in yellow the lunar distant retrograde orbit. It's not a orbit, it's a whole family of orbits. It's 70,000 kilometers plus or minus 20 kilometers-ish, and that it's relatively stable. We actually hadn't studied that orbit in a long period of time until actually the ARM mission came along. We were looking at a place to park the asteroid that would take very little delta V to keep it there. And we went back to a lot of the trajectory analysis we had done and went back and rediscovered LDROs. It's a good staging point. And what we found now is actually staging out of an LDRO, because it takes very little energy to keep something there. Again, that 70,000 kilometers, plus or minus 20,000 kilometers, it will stay there for 80 years with no energy input. That's really great when you're assembling something that you want to send somewhere else. So this whole discussion about Lagrange points versus LDRO and all that, quite frankly, it's kind of moot, because physics kind of tell us where we park things. And you see the intersection of LDROs transferred from that to L1, L2. These are all very minor amounts of energy to do that. So we can agree on a common area where we do assembly and kind of move on to the next decisions. At the same thing, on the Mars system, we don't know where to do staging out of. And we've been doing a lot of trajectory analysis for Mars. So what you see here is Mars equivalent gravity well. And you see Phobos and Deimos. What you also notice is Phobos and Deimos almost have no effect. They're kind of little blips on the Mars gravity forces. And in fact, any kind of missions to Phobos or Deimos are actually more impacted by the gravity of Mars than they are by their own self. But where to stage things out? So you get different approaches. Hyperbolic approach and departure in the green line is one thing that you could do. You also have 1 Sol and 5 Sol orbits. And these are a function of what kind of in-space propulsion system do you use. Do you use a multi-stage approach where you bring multiple chemical stages and or multiple chemical and SEP stages, and you could easily get into kind of a 1 Sol orbit with that kind of architecture? Or do you do a hybrid stage where you actually combine the best of chemical and SEP into a single stage and say a LOX methane SEP stage? Then you can get into something like a 5 Sol orbit. relatively easy. And then you're looking at five solar orbits as your staging point. We haven't decided where we stage at Mars, but this is the type of analysis that's going on by all the teams and internally and externally. So when we talked about co-manifesting, to give you a perspective of what that looks like, we have an exploration upper stage that's going to be added to SLS. That increases its overall launch capacity. We don't need that, obviously, to throw just Orion, but we want to be able to put cargo with it. So here's a couple of variants of kind of what the fairings look like in these different configurations. One of them is with Orion with a habitation module sitting up underneath it. One's another with a robotic lunar lander, say, and a short duration HAB module grouped together that could also fit in there. And they got a couple blunt nose kind of fairing configurations. This is what it would look like if you have a scientific mission going out to an outer planet, or something like in the ARM mission as well. And then we're doing further analysis on fairing optimization for long duration for things like large telescopes and the habitation systems we need for Mars, and trying to figure out, is it an 8 meter, 10 meter? Again, try to drive commonality to get some cost out of the system to figure that out. But you can imagine that if you flew Orion with a habitation system like this in here, over 3 to 4 launches of this kind of configuration, you can aggregate the volume you need for habitation for a transit to Mars in that kind of launch configuration, where you don't have a dedicated launch that's separate just for a HAB, but rather you aggregate it over time. So things like that are being looked at. To give you perspective on solar array and solar electric propulsion, ARM's kind of in the middle of its class. Deep Space One and Dawn are over there as things that we've done in the past and where ARM's going to get us. And then what we need for solar electric propulsion for cargo and that hybrid stage for Mars crew, that's the power levels that we're looking at that we need for those class missions. Another simple way to look at it, if you look at a comparison with Space Shuttle main engine, there's 3 of those, versus a 300 kilowatt subsystem. There's ISP and thrust up here that you have. If you have time on your side, the burn time there, if you have time in order for the transit, and you can actually use that as your dial, you can actually get the equivalent energy and out of that kind of propulsion system as you would out of a traditional chemical system at a fraction of the propellant mass. So this is, in a very simple terms, what it means. So the equivalent of 32,000 kilograms of launched mass will get us the same amount of total energy if we have time to do the pre and placement of the cargo. So this is where some of that comes into some of our design analysis. So we do this EMC not as a whole series of decisions, but rather a series of questions that are kind of asked every year. And the questions that are going through this year are things like, how do we do this overall pioneering kind of approach? And ISRU, what is the role of in-situ resource utilization and an overall architecture? So that's one of the pieces that we're looking at. What are the objectives, engineering, and operational considerations for a landing site? And in fact, we have a landing site activity that I'll talk about going on. There's a whole other sequence here. We talked about the asteroid redirect vehicle and pre and placement of cargo, and I'll show you that, how it scales up. And then how do we look at commonality of habitation systems for short duration HAB is another one. So if you think about coming off the surface of Mars versus a Mars vicinity taxi, if you're in that 5 sol orbit, how do you go from a 5 sol orbit to actually going to the surface? Those may be short duration habitation systems. To even our initial exploration HAB that we would need in deep space, where are the commonality of that? And we're doing a lot of commonality and modularity studies as well. So there's a whole series of questions that we have going on, and I'll touch on the ones I just highlighted. In situ resource utilization. How do we go from what our baseline assumption, which was creating an oxidizer from the atmosphere of Mars, to now knowing that there's a robust water sources on Mars and other bodies like asteroids and the moon, and how do those actually play into the logistics challenge that we have? And how do we build that up over time to be our sources of consumables and propellants that we need for overall architectures? And that's one of the key things that we're looking at. Things like our resource prospector mission that's in formulation right now is a key measurement that we're looking at. We know water exists with pretty high confidence, but we don't know how it's bound. We don't know its distribution and all that on the surface. But how do we understand that better so then we can start counting on it for our architectures? Site selection, we're actually working between us and our science mission director colleagues on actually determining which sites are the most likely ones that we want to send humans to. So over the course of this next year, we're going to have a whole series of workshops and public engagements to actually determine which are the high likelihood sites and down select the sites that we would want to actually target for every future science mission going to Mars is our areas of interest where we'll get the high resolution imagery, get all the data that we want from a civil engineering perspective along with a scientific perspective to actually do that pre-emplacement over time. But it's really key that we narrow down where we're looking at Mars now in order to concentrate our scientific assets on that capability. So to show you a little bit of how things scale up on the solar electric propulsion, on the left-hand side is the size of the solar electric propulsion bus as it's currently being thought about for the ARM mission. It's 50 kilowatts, 40 kilowatt electric propulsion system, and 10 tons of xenon. If you were to take that and scale it up to a multi-stage approach where you have a full chemical stage and you have a full solar electric propulsion stage. That solar electric propulsion stage would look like 190 kilowatt solar arrays, 150 kilowatt electric propulsion system, and 16 tons of xenon. Now, instead of having two stages, which is two development efforts, how do you put those together into like a hybrid stage? What does that look like? And then what does its packaging look like? And how would it be launched into space? And those are the specs for the hybrid stage. And there's two concepts there. You could literally take two of the ARM type buses and put them together underneath a chemical stage. And you can get a packing efficiency that fits in a 10-meter fairing on an SLS. Or you could actually repackage it and get a little more elegant in the engineering, and you can get down to 8.4 meters. In a fairing size. So these are the trades that we're actually doing with us and even industry right now to figure out what that is, what does that in-space propulsion stage look like. All of this though for in-space propulsion, landing site analysis, all this comes together in figuring out how do we actually land. You always hear the number, we want to land 40 metric tons on the surface of Mars. Well, how do you get the 40 metric tons? Well, it happens to be we took the largest indivisible payload unit, and which happens to be your ascent vehicle to get home. That's not something you want to DIY on the surface of Mars to get back home. Crew kind of frowns on that. If you take that, and with all the propellant that you need in it and such, it's about 35.5 tons. And that's where that 40-ton number came from. You combine that with the payload elements and the crew, you get to this 40-ton chunk that needs to get down to the surface. But if you think about in situ resource utilization, either your LOX, just the LOX side or your methane side, you can then get savings. So one of those things is if you have an ISRU plant just for LOX only, you can save yourself a significant amount of mass. So if your LOX is 19.2 tons, but it only takes you 10 tons of plant to produce that, now you can save yourself 9 tons of mass right there in a landed kind of increment. And then you get down to landers that are in the 27 ton to 18 ton category. If we're also producing methane from Mars once we get there, that will be a further reduction, and that's actually one of the pieces that folks are studying now as well. The other part is like surface propellant transfer. Could we just bring propellant tanks and do transfers? And that's another strategy, and you can get down to 15 tons or 18 tons in that scenario. So when people talk about what size of things do you want to land on the surface, you have to do your homework and analyze your launch capacity, your fairings, your in-space propulsion stages, this in-situ resource utilization. So what the Evolvable Mars Campaign teams, both internally and externally do, look through the entire trade set, all these architectures that other people are publishing to find new ideas, and then run through a lot of this trade analysis that we have. At the same time, we're looking at commonality of habitation systems. So you have two kinds of habs, things that you need to live for a short time, things that you want to live in for a long time. And you can look at how do you get and drive common elements. So if you think about an initial hab to allow you to live 30 to 60 days at an LDRO combined with Orion, you might be able to fit something like that in the SLS co-manifested space. But that kind of habitable unit could also be the basis of your logistics carrier. It could be the basis of your pressurized volume for a taxi to go out of that 5-Sol orbit to Phobos and do visits there. It could be the same pressurized volume that you have on a surface mobility unit once you get to Phobos or the surface of Mars. And it could be the same pressurized volume that you need for your ascent vehicle. So where is that kind of commonality approach there? The other side is long duration hab. So if we just think about a very large hab that can actually support 500 days on the surface to Mars, or a transit to Phobos, or just your in-space transit that you need, where is a commonality from that perspective? Now, you don't have to pick one or the other. You can look at it from a modularity perspective as well. So you can look at it from, do you build something up that's out of that large element that then follows all the way through? But then you have to design this very large habitation from day one. Or do you want to incrementally build it up over time? But then you go back to that landed mass chunk, and how do you want to aggregate your hab on the surface of Mars or not? So these are the types of trades that are ongoing out there. So we bring back, it's not just NASA. We talk about this ecosystem. It's more than just NASA. It's not just NASA and its contractors. There's an entire industrial base of the space economy out there. So how do we engage them? And I talked about these commercial strategies and engagement strategies we have with them. We have, the most recent announcement was our Next Step BAA. It's a broad agency announcement. It's a way to engage in funding mechanisms with the external sector that we don't define set requirements like you normally do a requirements definition, but you rather set performance goals or objectives, and you don't tell people how to do it. So we ask the commercial sector and academics and industry as a whole, how would they approach advanced propulsion systems? So how do we do some of these larger thrusters that we want? How would they approach habitation, including the life support elements that we have? And then, because we also have a large number of strategic knowledge gaps that we need to know about destinations, there's also this whole surge of small satellites occurring. So how do we leverage that advancement in small satellite technology that they can leverage here in LEO and GEO, and then we can use it to send missions out into deep space using CubeSats and such. So we put out a call, and what was unique about this is these were fixed price contracts. We actually required them to put their own money, their own skin in the game, at half the price of what they were asking us to pay for. So these weren't just your idle standby folks. They're actually putting just as much money in it as NASA was. And we got a very, very robust response. We ended up selecting a couple CubeSat missions. These are 6U CubeSats that will also fly on EM1, along with the ones that we're building here at NASA, including BioSentinel that's being built here at Ames. One's by Morehead State University in partnership with Busick for their propulsion system. And another one is Lockheed Martin, which has a whole cadre of technologies that they're advancing. These are going to help us get some of the measurements that we need about resources, lunar resources specifically in this case, as they do and conduct their missions. On the propulsion side, we had 3 different companies we selected. So talk about ARM. We talk about 10 kilowatt per thruster kind of is what the performance is of the ARM class SEP system. I talked about scaling up to 300 kilowatts. Well, you can do that by just ganging together a whole 10 kilowatt and have 30 of those on the back end of your spacecraft, or you could go to larger scale single thrusters. We believe there is probably an optimization that at some point we want these larger scale thrusters in the 50 to 300 kilowatt range. And you notice the companies here, Ad Astra, Aerojet, and NMS&W, they've done a lot of work on their thruster designs and power management systems over the past couple years, but none of them have actually demonstrated continuous thrust at a reasonable amount of time that's useful. So what these awards were 3-year awards. They have to demonstrate 100 kilowatt for 100 hours continuous thrust with full thermal management and control of their thruster. This will get them at a TRL 5, 6 level that is then in the competition range for next upcoming design trades we have. So how do we, this is the seed corn kind of feeding some of that. And some of these are we know nested Hall thrusters have been around for a while. That's Aerojet's concept. Plasma thrusters, Ad Astra has been doing quite a bit of investment with that as well. Now it's time to actually not just talk about it and not do just the engineering, but actually do the test and get the data for it. On the habitation side, I'll split it into kind of 2 sections. We talk about habitation, the module that you'll live in, and then the life support that will keep you alive. So on the habitation side, we awarded to Lockheed, Bigelow, Orbital, and Boeing. And what we're trying to do is that commonality, modularity kind of discussion I had. What is that low Earth orbit commercial strategy versus our habitation strategy we need for deep space? Where's the Venn diagram overlap with what industry wants and is capable of doing? So we're asking all 4 companies to give us their independent approaches to optimizing for meeting our NASA need, the exploration need, but at the same time maximizing their potential to use it for other things like low Earth orbit commercialization. And we're doing this right from the get-go instead of kind of after the fact. So we're trying to get that industry participation from day one. So these are some of their graphical mock-ups of what their ideas look like. On the life support side, we did 3 awards. 2 of them are related to kind of architectures. How do you put together a modular habitation system? Was the basis of Hamilton Sundstrand's proposal. Hamilton's got a long track record in building the life support systems for ISS and also Orion, but they're not modular in nature. So how do you actually readdress the modularity of life support systems? Orbitech, very interesting. There's a lot of talk about bio and chemical and electrochemical systems working together in life support. The last study we had on biology-based life support systems was at a time when LED lights were not invented yet. So if you had to keep your biology alive with those heavy, older ways of doing that, it didn't trade well in our overall architecture. So this is a basis of getting Orbitech to actually update our integrated system analysis of what does it really mean when you say I'm taking a biology-based life support system. And then Dynetics. One of our primary challenges we have on the space station is our CO2 removal. It's one of our most troublesome systems. So Dynetics actually proposed a new way that actually separates the CO2 from the other undesirable gases. And this is, what you see there is one rack that would fit in one rack unit of the space station. And the consumables for that would be on the order of something about 6 inches by 6 inches by 6 inches for an entire duration trip to Mars. This is drastically changing the equation on how to remove CO2. And that's going to be really intriguing to see their advancement they make over the next couple of years on that. So my whole purpose of today is to actually give you a little more technical detail behind what our real planning that's going on in human spaceflight, and actually to draw your attention away from the squiggly lines up at the top and actually think about the bottom part. What does it really mean to go from Earth reliant to Earth independent? And how do we make decisions and technology investments and mission decisions that maximize our ability to live off the planet for longer and longer? Because I think that's our fundamental challenge. And then if we prove that we do that, then the destinations are all open to us. So with that, I'll turn it over for questions.
So if you have questions, please line up on the microphone in the middle of the aisle. One question and be succinct, please. Thank you. So let me ask a question until we get other questions coming in. At one point, as you have an evolvable system, you have to make a decision and say, okay, now we stop with our current technology and we go to that location, whether it's Mars, ARM, or any of those locations. How are you planning to determine that stage in the evolvable design scenario?
The basic premise of that is make no decision before you have to. And that just basically means that we do a lot of technology roadmaps and we have pre-deceived kind of decision points or when we think we need to make a decision. But it's very important that we actually make decisions when we really have to and not close the on-ramps of other new solutions too prematurely and keep on investment. Now, we can't fund everything either. So that there's a kind of a tug of war on being able to fund everything versus making some of those down select choices. So through some of this trade analysis that we have, we will narrow down the areas, but we won't narrow down the specific implementation or the technologies that we actually choose. And we'll allow technology advancement and scientific understanding to advance and still make future decisions as well. So we got to fight against laying out every mission from here to Mars and actually say, well, we already decided what the mission is 15 years from now. Well, guess what? It'll be wrong. So let's not make that decision now, but rather put that off as long as we can in order to allow technology to continue to advance. So.
Hi, my name's Thomas Graham. I'm an intern here for the summer, and I liked your presentation. I'll say that. But there's a lot of talk about going to Mars with people, sending a lot of research equipment and doing a lot of research on Mars, looking for life. And with respect to the proving ground idea, where do you see lunar missions in that regard? And what do you see? What is your opinion on the importance of going to the moon or using the moon or lunar orbits as this proving ground?
Yeah, so the basic premise of the Proving Ground is lunar orbit. So that is our staging point there. So the lunar environment is intriguing to us in many ways. Not as a place to go back and plant another flag and footprint, but rather as a place that is a source for resources to implement this reduction of logistics from Earth. So if and when we can actually capture resources, be they lunar resources, asteroid resources, Mars moons resources, we should be going after this kind of resource analysis piece and how that trades into our architecture. The preliminary, all the scientific data that we have to date points to a pretty robust water environment that exists on the lunar surface. We don't know how it's bounded. We don't know how hard it is. We don't know how to extract that material, what it will cost to do that. We do know that the dial of impact on our overall logistics chain to Mars could be extremely significant. So it's not something to abandon at this point in any means. And that's actually why we've been keeping things like these 2 additional CubeSat missions that I just showed you, but even more so going to the surface in a mission like Resource Prospector to actually get the surface validation of that measurement and how is that water distributed and how hard will it be to actually utilize an overall architecture. So yeah, I think it's going to be key. Resources will be key no matter where we want to go. So.
Thank you. Hi, Jason. When you make a decision, you have some notion of better or worse. And you also have some notion of technology that you use to analyze all the information at your disposal and say, I can quantify some decision as better or worse or possibly incomparable. So what is it that people are doing in order to take all the analyses, all the trades, all the architectures, and to put them into, if you like, one decision support system that helps you understand, even if I can't say this is best, what is better and what is worse? How do you actually do that?
Yeah, so to me, it's, you can boil down all the capability areas that you need to sustain human presence and send them out there. There's different ways to slice it. The National Research Council does it one way. NASA has its roadmaps another way. However many capability areas that you have. And you can actually analyze those capability kind of decisions through almost like a Pareto analysis, finding the optimal points on curves for the best or worst from an engineering perspective that you have out there. So it's good to have sound, good engineering analysis of what from a technical performance basis is best. That not necessarily will be the thing we do, because then you also then bring in the alignment with industry, commercial use of that, the application of the technology beyond just NASA's requirement for it, international contributions. So you have this very multi-variable problem that it's very difficult to actually determine better or worse, and I would argue it's impossible to determine best because it's an unbound problem. And so if you analyze that by capability area, you can make good enough decisions that you at least have a confidence level that you've not made a decision that will close off some future architecture down the pipe. This is a delicate area, though, so this is an area kind of ripe for all of you in the room to actually help with. I don't think we have good decision logics and decision trees that do this kind of things. We're really good at systems engineering when we have a bounded problem, but how do you do systems engineering when you have an unbounded problem? And that's what we're facing. And I don't think we should try to bound it. So that means we have to figure out the other part. So I don't know if that answers your question, Jeremy, but I think some of your guys' algorithm development and decision type things are key to some of that too. So, yes.
Hi, Jason. Ryan Vaughn. I'm a system engineer here at Ames. Work on Resource Prospector. So, I have a question about what kind of research is in place for long duration exposure to radiation, both on transit and in HABs on Mars, and what kind of work can be done between now and these proving grounds to mature that.
Yeah, so for the radiation environment piece, I boil it down to kind of 3 categories. First is we need to actually know, no doubt, what the radiation environment is. So that's the measurement piece. So with that, we've actually got a whole team of radiation dosimetry, both internal to NASA and outside of NASA, working together on everything from Mars Curiosity instrument to the ISS instruments. EFT-1 flight of Orion had a radiation sensor on it. and even things like BioSentinel that's being built here as a CubeSat. There's commonality in all those instruments, and there's definitely commonality in the team, so that we're actually getting the radiation, no doubt, measurements of what the environments are going to be. And in fact, on Curiosity, we monitored we had our radiation instrument on the entire transit to Mars, and we've had operations on the surface of Mars as well. And as we get these next instruments in orbit around Mars, from there, we're actually going to get now orbital characterization of radiation coupled with the ground characterization, and now we can figure out directionality and atmospheric effects and all that. So that's the dosimetry piece, and I think that's well in hand of really understanding the environment. The next is actually modeling the actual entire solar system effects and the heliophysics and all that. And that's working closely with our science folks in heliophysics and figuring out when you have an event, what does that event mean and how does it propagate and how do you do real-time operational warning systems. And right now, our modeling could be a lot better. And there's considerable effort on taking that kind of scientific operational data, measurement data that I have, and then propagating that into our models that then carry through the solar system and understand what even down to, say I was standing in the middle of a HAB, what is the HAB's effects and actually translating that all the way down. There's error bars on every one of those steps, and the modeling needs to improve. And then there's the human research program side of this, of once you actually do get the radiation effect to that individual, what does it mean to them and how do you mitigate that? And there's a whole cadre of research going on in the human research program that I can't talk about as much as they could, but the levels that we're seeing, even in a Mars transit, are within reasonable limits. These are not hard achievable things. The PI for Mars Curiosity put the estimate of the lifetime risk at 5% if you would have been on Curiosity yourself. Our current limit is 3% based on radiation worker tolerances we have. 5% of your total risk of lifetime cancer. So that puts in perspective the risk levels that we're talking about. So.
Would it be possible and/or better to use nuclear power sources for these hundreds of kilowatt electrical supplies that you need? Would a small nuclear reactor have a higher power output to mass ratio? What is the thoughts on that?
Yeah, so there.
Other reason you would not use nuclear power?
Yeah, so nuclear is still in our trade space, and it's in our trade space in 3 areas. Nuclear thermal propulsion. So anywhere you saw a chemical stage, there is still a potential of trading out that chemical stage for a nuclear thermal propulsion stage. And in fact, we're still doing the research on fuels within AES, the program I run. And we're advancing the fuels technology and recovering what we lost from NERVA and actually moving forward in our understanding of the fuels piece for nuclear thermal rockets. The rocket is relatively simple, not to underestimate the rocket folks, but it's a heat exchanger. It doesn't have the complexity of a normal rocket, but so the fuels are the hard piece there. Surface power is the other area. If you're doing all this in situ resource utilization, you're probably going to need significant power on the surface. So surface nuclear power is an area that's still going on, and you have investments by our Space Technology Mission Directorates and things like Kilopower is their project. They're looking at a 400 kilogram, 1 kilowatt nuclear reactor. And how does 1 kilowatt doesn't scale? I mean, that small of a size isn't worth it at that mass, but you need to figure out, we don't need 40 kilowatts at a single chunk of nuclear power, but maybe a 10 kilowatt. And how does that scale and what is the incremental cost? And that's one of the investments that's going on. We may not need it for the initial missions, but we will need it over time. And your last question was nuclear reactors, nuclear electric propulsion, or nuclear power there. If you look at multi-megawatt reactors on that kind of scale, when you're getting several hundreds of kilowatts and such, that is a potential solution. Most of those reactors, though, the designs for those reactors run at temperatures that even our ground-based nuclear folks have not seen except in runaway conditions. So you can look at reactors as a function of heat. And so that's a new development effort, and that could be a multi-billion-dollar development effort. So we've been concentrating on using solar electric propulsion, and we believe in this scale, the 300, 400 kilowatt range, is reasonably achieved by solar electric propulsion. If the state of the art today of solar electric propulsion, if you look at the space station arrays, you could generate the same amount of power the station has with 20% of the acreage. So the advancement of solar array technology has come along a long way. So if you think about station, what we need is the acreage the size of the space station. But that same acreage would produce 5 times the amount of power the space station has. So it is something technically achievable today. Now, at what cost to launch that kind of acreage is the challenge. So right now, we've chose not to do the investment in the in-space nuclear, but rather concentrate on the engines to get there if we want to trade out nuclear thermal propulsion, and the surface power as our first steps, and then use solar electric for the transit piece. It doesn't mean that it couldn't come on board at some point, though.
So please join me in thanking Jason for an excellent talk.